In 2005, Barry Marshall and Robin Warren were awarded the Nobel Prize for proving that Helicobacter pylori causes peptic ulcer disease. But the real mystery isn't how they made the discovery, it's why it took so long. Because this bacterium had actually been observed in the human stomach as early as 1875. For over a century, evidence accumulated, then was dismissed, forgotten, or explained away. Not because of bad intentions or bad data, but because it didn't fit what science already believed. In the end, it came down to one man drinking a solution teeming with live bacteria to prove what hundreds of papers and decades of research could not. This is the story of one of the most delayed discoveries in medical history, and the self-experiment that finally forced the world to listen. Gastric ulceration was known to the world of medicine since the medieval ages. In 1586, Donati Marcello, an Italian physician, described gastric ulcers for the first time in detail. The function of stomach acids was described by William Prout in 1823. The first recorded study to suggest that peptic ulcers might be caused by bacteria was published in 1875 by two scientists, Botcher and Latoul. Others soon began to see the same thing. In 1881, Klebs reported spotting bacteria-like organisms inside the gastric glands. In 1889, Wallery-Jaworski described spiral-shaped organisms in human stomach washings and even suggested they might be involved in gastric disease. By the end of the century, these sightings multiplied. In 1892, Bizzozero observed spiral organisms in the stomachs of dogs. In 1896, Salomon found similar organisms, likely spirochetes, in the stomachs of cats and mice. There was a growing body of evidence, and for a moment the bacterial hypothesis seemed to have a future. But science doesn't happen in a vacuum. In 1905, F. Rigel suggested that ulcers weren't caused by microbes, but by excess acid. Again, this was not a new idea. It was first suggested by Kussmaul, who in 1869 had developed a method for intubation of the stomach. Then in 1910, Croatian Karl Schwarz coined a phrase that would shape medicine for decades: no acid, no ulcer. It was catchy, it made sense. And when antacids were found to relieve ulcer symptoms in 1915, the acid theory didn't just gain support, it gained momentum. For decades, both ideas coexisted uneasily. Some researchers still observed bacteria in the stomach. Some even experimented with antibiotics. But the acid theory had a clear treatment path, and with it, clinical success. Then in 1954 came the study that changed everything. Dr. Eddie Palmer, an eminent gastroenterologist, published an article titled Investigation of the Gastric Mucosa Spirochetes in the Human. In this study, he summarized his findings from 1,180 stomach biopsies. He inferred that no bacteria could survive the strong acidic conditions in our stomach. Based on that, he concluded the earlier reports were all due to contamination, and the scientific community believed him, given his status and the rigorous scientific methodology he used. That one study didn't just end the conversation, it shut the door on it entirely. What Palmer didn't realize, though, was that he'd made a critical mistake. He used a Gram stain, a common lab technique, but one that doesn't reveal Helicobacter pylori. A silver stain would have worked, but it was rarely used on stomach tissue back then. The result? The bacterial theory was buried, but not completely forgotten. In 1958, in a small town in Greece, a doctor named John Lakoudis began treating his ulcer patients with antibiotics. It worked. He tried to publish his results. He was rejected. He presented at conferences. No one listened. In 1968, he was even fined for using antibiotics on ulcer patients. His discovery, too early, too unconventional, was lost in the noise. Meanwhile, the acid theory dominated until it started to crack. In 1978, a major gastroenterology meeting revealed a growing concern. Acid suppression could control ulcers, but it couldn't cure them. Something was missing. In 1981, Barry Marshall, a young medical researcher, joined forces with pathologist Robin Warren in Perth, Australia. They noticed ulcer patients often had spiral-shaped bacteria living in their stomach lining. By 1982, they began testing the link between this bacterium Helicobacter pylori, and peptic ulcers. In 1984, they published their study, and they were mostly ignored. The ghost of Palmer's study still haunted the field, so Marshall did something wild. He drank a beaker full of Helicobacter pylori. It was a last resort experiment. Marshall had spent years arguing with skeptics, but without an animal model, there was no way to prove that H. pylori caused disease. So he took matters into his own hands.
And so I continued the experiment until over the weekend, until Tuesday, and then I had a further endoscopy and some testing. Then I started taking antibiotics.
He first confirmed he was free of any H. pylori infection with an endoscopy. Then in July 1984, he drank a cloudy suspension of the bacteria cultured from a patient with dyspepsia. Within 5 days, he had symptoms of gastritis. A follow-up endoscopy revealed severe active gastritis, which is a precursor to peptic ulcer. Helicobacter pylori had caused visible damage in a previously healthy stomach. The implications were enormous. Gastritis and eventually ulcers were infections, not just reactions to acid or stress. In 1985, Marshall and Warren published their results. And this time, the field took notice. The tide had turned. In 2005, Marshall and Warren were awarded the Nobel Prize. But this story leaves behind a haunting question. Why did it take so long? How did so many smart, well-meaning scientists miss something so crucial? In the next part of this video, we'll explore a strange idea that may help explain it. Philosophy professor Kevin Zollman published an intriguing article in Springer Science in September 2009. It was titled "The Epistemic Benefit of Transient Diversity." In it, he explored a fascinating question in network epistemology: how groups of individuals, each with limited knowledge, can collectively arrive at the truth. What he discovered was both unexpected and deeply relevant to the story we've just told. Let's say doctors are trying to figure out which theory better explains peptic ulcer disease. A doctor has two options. One is the acid theory, the other is the bacteria theory. She has to decide which treatment to recommend. If she believes in the acid theory, she will use antacids. If she believes in the bacteria theory, she will treat her patients with antibiotics. Now, when we talk about belief here, we mean the doctor's judgment about which treatment is more likely to succeed. Doctors, of course, don't want to knowingly harm their patients, so they treat based on what they currently believe is the best option. Suppose our doctor believes that the acid theory is correct. She gives the patient antacids. Then, depending on whether the treatment works or fails, she updates her belief about how effective that theory is. But since she didn't try the antibiotics, she doesn't update her belief about the bacteria theory. However, doctors don't work in isolation. They talk to each other. They share their results and update their beliefs based on what others have experienced as well. So let's imagine a group of doctors, each one connected to others in a network. These connections represent the exchange of information. Each doctor shares how their treatments went and uses the data from others to refine their own beliefs. In his work, Zollman studied 3 types of networks. The first is called a cycle, where each doctor is only connected to 2 others. The second is a wheel, where one central doctor connects to everyone else. The third is a complete network, where every doctor is connected to every other doctor. What Zollman found was quite surprising. As expected, the more doctors you have in the group, the better your chances of eventually discovering the right answer. More doctors mean more trials, more data, and more opportunities to learn. But here's the twist. The less connected the group is, the more likely they are to reach the correct answer. There's a graph that shows this clearly. It plots the probability of reaching the right conclusion as the group size increases. All the curves rise, showing that bigger groups perform better. But the curve for the cycle, the least connected network, stays higher than the others throughout. It performs better than both the wheel and the complete network. In other words, doctors in a sparsely connected group figure out the truth more often than those in a tightly connected one. This surprising result is known as the Zollman Effect. To get a sense of why this happens, let's think about a densely connected network. Imagine that one of the most well-connected doctors believes in the acid theory, treats a patient with antacids, and sees a positive result. That result spreads quickly through the network. Other doctors start to believe in the acid theory too, simply because someone influential succeeded with it. This is very similar to what happened when Palmer published his results. He was a respected figure, and his findings reached nearly everyone in the field. Many doctors updated their beliefs based on his work alone, and the bacteria theory was largely abandoned. Now compare that to a sparsely connected group. In this case, the same doctor believes in the acid theory, treats a patient, and succeeds. But because she only shares her result with a few others, only 1 or 2 doctors update their beliefs. The rest of the group still holds a mix of views. That allows another doctor, who happens to believe in the bacteria theory, to try antibiotics. If she sees success, she updates her belief, and so do her few neighbors. Because the group remains more diverse in belief, it has a better chance of discovering the right answer, even if that idea started out as the minority view. Of course, the real dynamics are more complex, but the key insight is this. When the group is less connected, early successes or failures don't spread too quickly. This helps protect the group from getting stuck on the wrong idea too early. He argued that an optimal level of initial rigidity in the diverse, competing scientific theories is crucial for the progress of human knowledge. While this rigidity might not always benefit individual scientists, like in the case of Lycudes, it can ultimately serve the greater good. As we continue to advance in science and technology, we must find ways to preserve diverse perspectives for long enough to let the truth emerge. Thanks for watching. If you enjoyed this video, please consider leaving a like and sharing your thoughts in the comments. And don't forget to subscribe to MentisModo for more. See you in the next one.